right? All the stars that well, not all of them, well, most of the stars that we can see fit very nicely in this area called the main sequence. You see the slope ring down here, right? And stars actually spend most of their life on this main sequence. Now, when they're in that main sequence, the nuclear reactions that are occurring in them are mainly what's known as proton-proton reactions, right? Where you take two hydrogen protons and they get fused together to form helium-4. Okay. Right. Now, the story changed a little bit after that. You see these little areas in the upper right where you have these had giants and what they call supergiants. That's when the star starts to exhaust its fuel and loses pressure on the inside. All right, because you have to balance out. Remember how it stars form. You have a huge amount of masses crushing in. If you don't balance that out with something pushing out, which was the energy from these fusion reactions, they just continue to crush in and crush in and crush in. And how tightly it gets crushed depends on how much mass you originally started off with. Okay, so now we made that analogy. Let's go into the next step. So let's talk about that proton-proton interaction, because all the stars have gone through that. That's part of their life cycle. Keep in mind, the more mass you start off with, the faster the rate that proton-proton nuclear reactions happen. Right, so the really big stars, they're going to burn through their life really quickly, while the smaller stars, they're going to burn through their life slower and cooler. Okay, so let's keep that in mind as we go forward. Okay, so there's 3 steps to the proton-proton chain. The first one is, as I said earlier, we're going to fuse 2 hydrogens to get deuterium, right? Nucleus form, and it works like this. You have that environment inside of the core of the star. There's tons of hydrogen. It's gotten ionized, so it's just kind of like protons. They're forced together through the energy inside of the core. What happens is very amazing, actually. One of the protons turns into a neutron, which I read about that, and I was totally like floored. I was like, wow, okay. So in the process, energy is created. And that's where the sun's energy comes from. But what type of energy? It's going to be different energy depending on what type of reaction we're talking about here. So in the first case, with the proton-proton, we're going to end up with a neutrino and a positron. Now, positron is an antimatter particle. And I don't know if you guys watch sci-fi, but if you ever seen what happens when antimatter hits matter, it completely annihilates into pure energy. Right. So we have all this energy coming out of this reaction, right? That energy, some of it, it takes a long time to get to the surface of the sun. I have to tell you that, but it does get there. And there's so many of these reactions going on that even though it takes a long time, there's a continuous flow of energy out of the sun. So now let's go to step 2. What happens after that? Okay. Step 2. Remember those deuteriums we had gotten before, those nuclei, right? Now you take a proton, gets fused with one of those deuteriums. And from that reaction, you get more energy, right? But this time in the form of gamma rays. And you also get what's known as helium-3. So that's we end up there. So the deuterium forms, fuses with the hydrogen, another hydrogen proton. We get gamma rays, more energy, and helium-3. Last and final step, step 3. 2 helium-3s. So that last step that we went through, it has to happen at least twice. Trust me, it happens a lot more than that in the core stars. Right? You're going to end up with 2 helium-3s getting fused together to give you helium-4, and right back from where we started from, 2 hydrogen protons. And then the process starts all over again. Okay. Now, what happens after that? It depends on the mass. Remember I said that the more mass, the harder and faster these reactions happen. Okay, so if it's a small star, it doesn't have enough mass to generate the heat to go further than that. Meaning it cannot create more fusion among the helium. Then that's it. It lives the rest of its life, and when it runs out of fuel, it'll turn into a white dwarf. However, if it does have more mass, it goes into the heat builds up and builds up and builds up until it hits a point where it's around, I believe, 100 million kelvins. And then we go into this process of, oops, skip the, yes, 100 million kelvins. And we go into this process of what they call helium burning. Okay, we're going to get into that in a second, and there's a nickname for that is a triple alpha process. But before we go there, I just want to take kind of like a side and go over, take advantage to go over something that I thought was very interesting in the book. You know, in my experience in college, I've heard of Einstein's equation for energy E equals mc squared, right? I know that nuclear physicists use it. I know it's used in different areas within that field, but I've never had the opportunity to actually um, lay it out this way. So I'm going to take the opportunity to do that. Okay. So as we said, we start off with hydrogen, and remember we had to do it. We had to do this two times. So we two hydrogens for each set, right? So that's four hydrogens, and we end up with a helium. Now, what happens is, let's say, for example, we have a kilogram of hydrogen, right? We're going to end up with something around 0.9929 kilograms of helium. And that goes against the laws of nature. We can't lose mass somewhere. So what happens? The mass actually gets converted to energy, right? So you get from 1 kilogram of hydrogen, using the star, you get 0.9929 kilograms of helium, and the other 0.0071 kilograms of mass gets converted into energy not by, but which is described by Einstein's energy equation. Okay, so let's go ahead and do that calculation to see exactly how much energy do we get from this 0.0071 kilograms of mass. All right, so you see here on the screen, we have E equals mc squared. That's the famous equation where E equals energy, m equals mass, c equals the constant speed of light, which is in meters is 3 times 10 to the 8 meters per second. Right? We plug those values in. M is our mass that we described earlier. It's 0.0071 kilograms. We have the speed of light 3 times 10 to the 8 meters per second squared. That's going to give us, in joules, 6.4 times 10 to the 14 joules. That's for one reaction, right? That's a lot of energy. For a kilogram, that's a lot of energy. And now we begin to understand how the sun is able to provide this constant stream of energy because it's creating this huge amount of energy. All right. So now let's get back to what happens with the larger mass stars, right? We already know what happens to the lower mass stars. Once they burn up the helium, they're gonna, once they burn up the hydrogen, they're gonna end up just expanding, right, into red giants, losing their outer shell, and you'll end up, when it's all gone, when it's all said and done, you'll end up with a white dwarf, right? Now, for the more massive stars that have enough gravitational force to create that energy and heat inside of it, they begin the helium burning process now, right? This is called the triple alpha process. And watch how this works. Basically, what happens is we have two heliums fused together to form an element, right? And then another helium, a third helium comes in and forms another element. Okay, and now let's walk through the process. So two heliums come together, and remember, the temperature inside has to be approximately 100 million Kelvin. Okay, so you have two heliums come together. They form unstable beryllium-8. Before that unstable beryllium-8 is able to decay, another helium comes in, fuses with the beryllium-8, and out we get carbon-12, which is a very stable element. Right, but it doesn't stop there. Okay, once we get carbon-12, another helium comes in, fuses with the carbon-12. Now, at this point, I just want to remember that we're connecting everything to the HR diagram. This is where you'll see the stars start to move away in their life cycle, away from the main sequence, right? And they're turning into red giants because the processes that are going on in the star, they burned up all the helium. They don't have the same amount of energy to push out. I'm sorry, they burned up all the hydrogen. They don't have the same amount of energy to push out. So now they're eating up their own helium. Okay, but they're still expanding. It's finding a new equilibrium. It's called hydrostatic equilibrium because the energy balances aren't the same. So now it's burning into the helium and just fusing the helium together with what? The carbon that it just made, right? So the carbon fuses with a helium. Remember, this is helium-4, not helium-3. We created the helium, I believe I said that. We created the helium-3, the two helium-3s created helium-4, and now we have helium-4 with the beryllium creating the carbon, and then another helium-4 with the carbon now creating oxygen. Okay, So the process continues. After the oxygen is heavier. What do you think is going to happen? If we have enough heat, we have enough mass to form that heat, we're going to go ahead and we're going to end up creating, what's it, silicon now? Yeah, silicon, right? Uh, no, I'm sorry, not silicon yet. It's neon after that, right? So the oxygen we add gets fused with the helium, and we end up getting neon. And then the neon fused with the helium, we end up getting silicon. Then the silicon, and it keeps going like that. And each fusion, we're getting energy out of the system. Not as much as we got before, so we still have this contraction of the core, right? But we're getting some energy out of the system, right? Once we get to iron, that's like the stars in its death throes. Okay, got the next one. Yeah, we got right. Okay, oxygen, silicon, and then we get into the iron. Right. Now you can see here that in the image, the iron's at the core. We're not getting any energy whatsoever from the iron, guys. We're getting some from each of the other elements, the heavy elements, but not from the iron. So we went from the star went from getting all of this energy from the hydrogen to getting a little less energy from the helium, to get a little less energy from the carbon. And now it's just using up all this energy. And once it starts producing iron, that's it. It's getting no energy from the iron, right? So we have this unbalance and it's getting greater and greater and greater. The forces are building up. The pressure from the gravitational pull is just crushing it more and more and more. Right. And again, you can see this because now we are completely off the main sequence in the HR diagram. We have red giants and super giants, right? And it's just not going to be pretty.